Hello again. This is Math 2231 coming to you from the College of DuPage, and the title of this lecture is Miscellaneous Spring 2023 LSA Solutions Year to Date. As always, please be attentive while watching this video. The first LSA that we need to treat here is LSA 4. We're to find the limit as x tends to 1 of the cube root of x minus 1 all over x minus 1. And we were also supposed to find this limit, and we were to assume that this limit from the left, as theta tends to minus 1 from the left of f of theta exists, and that we have this inequality for all theta, and we wanted to find what is that limit that we assumed exists. Okay, so the first problem of what we're going to do is we can't plug in 1 because we will get 0 over 0. But we're going to multiply by 1 in a clever way. So we're going to multiply top and bottom by the cube root of x whole squared plus cube root of x plus 1, top and bottom. And we're going to recall that a minus b times a squared plus ab plus b squared is a cubed minus b cubed. And we're going to realize that the cube root of x cubed minus 1 cubed is, if you cube both of those, you get x minus 1. And so when we do that multiplication using this identity, we get x minus 1 over x minus 1. The common factor cancels, and now we can plug in x to be equal to 1. And when we plug in x equal 1, we get 1/3 as our answer. It's worth noting that alternatively, we could have noted that using the alternative definition of the derivative that we used when we proved that if you're differentiable, then you're continuous, that f prime of 1 is the limit as x tends to 1 of the cube root of x minus the cube root of 1 all over x minus 1. And this is f prime of 1 for y equal f of x equal the cube root of x. So if we were to take this derivative, we would get the derivative of x to the 1/3 is 1/3 x to the minus 2/3. So again, the derivative is equal to 1/3. This situation is going to involve the sandwich theorem, or squeeze theorem, I guess we called it. And so what happens is the limit as x, well, first of all, we said this is true for all x. So the limit as x tends to minus 1 on this side is just going to be minus 1. In fact, you can plug it in. And you can plug it in on the other side too, and you get minus 1. So you see f of theta over theta squared is bounded between those. Now, since the limit of the top exists, that means that we could multiply all the way through by this, and we've said that f of theta is in between these two values, and this should have said limit as theta tends to minus 1 of f of theta is going to be minus 1, because both of these, when theta tends to minus 1, both of these are minus 1. So by the squeeze theorem, f of theta is, this limit is minus 1. Here we were to determine what values of k is this function continuous, and so the limit from the left and the limit from the right at minus 1 have to be the same. So let's do that calculation. So the limit from the left ends up being -4. The limit from the right ends up being this expression, and we can plug in x to be minus 1. So we get -4 is equal to minus the square root of k minus 1. We can solve this, and we find that k is 17. This was dealing with the bisection method, and we were supposed to say how many iterations were required, explain how we would approach this. There is a little subtlety happening because to solve cosine x equal x, you have to change this. To use a bisection technique, you have to change this to cosine x minus x in order to solve it. Now, those two things are equivalent, but that's fine. And then you were to use Excel to do this. So here we go with our solution then. So if we go and look at the possible error at each step, we say at the first one, the first guess, we could have an error of 1/2, then 1/4, and goes all the way at the nth step, it's 1 over 2 raised to the nth power. So we need this to be less than 1 over 1,000, And certainly if we take 10, we will be there because this is 1 over 10, 24. 9 won't be good enough because that's 1 over 5, 12. So n equal 10, and that's the worst case. So that's the answer to the first part of this problem. Now, note that in order to compare things to 0, we do need to reframe the problem slightly. And so we're going to be looking at g of x equal cosine x minus x. And you see the solution here, where we find the 0, is the same as cosine x equal x, but this way the process will work. And please note, my dear students, that g of 0 is bigger than 0 and g of 1 is less than 0. Okay, so this approach will work, and that's what we will do. Here are the steps. You notice that in 10 steps, the error got to be less than 0.001, and to 3 significant digits, it was 0.739, which is what we get if we look at the solution other ways. And I also ask you to show the equation Excel, and these are the equations that I used. And notice that I was looking at cosine of x minus x here. Okay, moving on to LSA 7, there were the first problem. This was one of 3 problems that were in LSA 7. So the first one had parts A and B. Them here. So here we want to find the radius of the largest possible circle centered on the y-axis that is tangent to the parabola at the origin, 0, 0, as shown in the figure, and the figure was shown on the previous page. This is called the circle of curvature, and you want to find the equation of the circle. Well, you see, if you set it up, the circle has to look like x squared plus y minus r whole squared is equal to r squared, and the parabola is y equal x squared. So you see, we can substitute for x squared y, and if we do that and move things to the other side, we have y minus r whole squared is equal to r squared minus y. Now when we expand things, we get this expression. We get y squared minus 2ry plus r squared. The r squareds will cancel out, and we can do factoring on this, and we get that y is equal to 2r plus 1. And so if we let 1 minus 2r equals 0, then we find that r is 1/2. And so that means the r that we had up here was 1/2. And so we graph y equal x squared, and x squared plus y minus 1/2 whole squared equal 1/4. We'll see that it does the job. It's that the circle is tangent at the origin, and that's what we wanted to do, and that was the equation that we were looking for. For the second part, we were to find the center 0b. So you see it's going to be centered on the y-axis that is tangent to the parabola at 2 points. So there's a point over here and a point over here. You want to find the equation of this circle and then graph it to show that it does what we want to do. So if we let xy be the point of tangency, then from the equation of the circle we know that x squared plus y minus b whole squared equals 1. And so what happens then is we can take the derivative of this, and we get 2x plus 2. This is going to be y minus b to the first power times dy dx, because that's the chain rule, is equal to 0. That means that y prime, the derivative, is equal to, and I'm solving this, I get x over b minus y. Now, that's for the circle. For the parabola, what we have is y is equal to x squared, so y prime is equal to 2x. So we can take this 2x and equate it to that and solve. So the x's will cancel. You get 2 times b minus y is equal to 1. And you can solve this, and you get that b is equal to y plus 1/2. Okay, so we also know from here that x squared plus y minus b whole squared is equal to 1, and y is x squared, so y plus y minus b squared is equal to 1, but we can do the substitution here. So we have y, and this is going to be y minus, but b was y plus 1/2 squared. Now y minus y drops out, and so you see that this is going to be y plus, we're just going to have 1/4 here is equal to 1. That means y is 3/4, and b is 5/4 because b was y plus 1/2. So you see, that means that this equation is x squared plus y minus 5/4 squared whole squared is equal to 1. So this is what we're going to graph. Here's the graph, and you can see it is tangent at the 2 points as we predicted. This is the second problem. You were to graph two parabolas, y equal x squared, and actually we're calling this y1 is equal to x squared, and y2 equal minus x squared plus 2x minus 5 on the same coordinate plane. And we want to find the equation of the two lines that are simultaneously tangent to both parabolas. This may have been a harder problem than some, but it's similar to ones that I've asked on high stakes assessments before. So y1 is equal to x1 squared at the point of tangency. And that means that the first derivative y1 prime is equal to 2x1 at the point of tangency, where x1, y1 is the point of tangency. And the coordinate on this curve is also x1, x1 whole squared. Now for y2, it works similarly. This is y2. The point of tangency is x2, y2. And so we have y2 is equal to minus x, so 2 squared plus 2x2 minus 5. You take the derivative, that means y2 prime is equal to minus 2x2 plus 2. And on the curve, this curve, y2, these coordinates look like x2, and that is minus x2 plus 2, x2 minus 5. Now the slope between this point, x1, x2, point of tangency, and the other one, x2, y2, is y1 minus y2 over x1 minus x2. But you see on the top curve, y1 was just x1 squared, and I subtract this one, and I note the change in signs, and then I divide by the change in x's. And so you see this slope is either going to be 2x1 on y1, I'm calling that equation A, or it is going to be, and here's where I got this, this is 2 minus 2x2 on the second curve. Now what I can do is, you see this is equal to 2x1, and the same thing is equal to this. Those are my two equations. If I subtract the 2, this will drop out. I have 0 is equal to 2x1 plus 2x2 minus 2. If you solve that, you get x1 is 1 minus x2. Hang on to that, but we're going to substitute this into the equation B. So we're going to substitute it over here and see what we get. So we're substituting that relationship for x1 and x2 into equation B. When I do that, I will get 1 minus x2 whole squared plus this over this is equal to this. Now notice, my dear students, that I only have x2 here, so this ends up being a quadratic in x2. And you can follow the algebra and multiply both sides by 1 minus 2x2 and simplify, but I find out now that x2 has to be 2 or minus 1. And if x2 is 2, then x1 is minus 1. If x2 is 1, then x1 is 2 from the previous substitution. So either we have this is a point of tangency, or these are the points of tangency. So the tangent lines are, I'm using the top equation, it's going to be y minus 1 is equal to, the slope is minus 2, we can calculate that, times x plus, or x minus a minus 1. Okay, so that is using this top point. The other one, the slope is going to be 4, and it's using this point, so it is y minus the y coordinate is equal to the slope 4 times x minus 2, and the whole of x minus 2. And if we look at the solution, we see that we do have the green tangents and the blue tangents as prescribed. This was the third one. You wanted to find a third degree polynomial, p of x, that is tangent to y1 equal 14, x minus 13 at 1, 1, and tangent to minus 2, x minus 5 at the point minus 1, minus 3. This is a third degree polynomial, and if we take the derivative, we get p prime is, this expression is going to be 3a x squared plus 2bx plus c. The d will drop out. Then I plug in 1, 1, I get these two equations. And when I plug in minus 1, minus 3, I get these two equations. So I have 4 equations and 4 unknowns. You know how to solve those. And if you solve those, what you will learn is that A is 2, B is 4, C is 0, and D is minus 5. The LSA 8 was about a satellite. You were to show that h was equal to r times the cosecant of theta minus 1. This is the picture. You wanted to find the rate at which h is changing with respect to theta when you're at pi over 6, and also figure out what fraction of the Earth's volume can be scanned. Well, if you look at the picture that we have up here, the sine of theta is r over r plus h. And so if you realize that you resolve this, that r plus h is r over sine theta, which is the cosecant. So r is equal to, or so h rather, is equal to r. This is cosecant of theta minus 1. Because if you factor the r out of here and you solve for h and you get this expression. Now we took the derivative in class and we found out this was the value of the derivative, and so that was now a satellite in orbit around the Earth can't see the whole Earth because of the perspective, and you can see here that you can only see the portion of the sphere that lies in front of the point where its line is tangent to the sphere. The closer you're to the sphere, the less you can see, and the line marking the point where the Earth begins curving out is called the horizon. And so what happens is, and this is what I asked you to show, but if the radius of the sphere is capital R and the distance of the observer from the sphere's distance is d, then simple geometry, I ask you to talk about the geometry though, reveals that the percent of the Earth's surface that is visible is 50% times 1 over r over d, and in our case r over d is going to be this ends up being 1/2 of 50% or 20. Now the reason this is true is that you can look at a picture like this and you can actually look at the geometry that unfolds, and this angle is the same as the angle that we were looking at, and so all of these are defined anyway. So this angle theta is the angle between the rays from the center of the sphere to the apex of the cap and the edge of the disk forming the base of the cap. So you see this is this is kind of like a polar ice cap. Now the area of the cap can be found according to this this formula. And so the area of the cap is the circumference times 1 minus cosine of theta, and the theta is the angle that we see there. And so that's going to be 2 pi r squared, and this is going to be 1 minus, and again, as we talked about earlier on the other slide, this is r over r plus h. So anyway, and this ended up being, the fraction that was 1/2. So this is 1/2 times 1/2, which is 1/4. This is LSI 9. You wanted to find a function of the form f of x equal a plus b cosine of c that is tangent to the line y equal 1 at the point 0, 1, and tangent to the line y equal x plus 3/2 minus pi over 4 at the point pi over 4 3/2. Well, At 0, 1, and you just plug it in, y is 1, and so you get a, the cosine of 0 is 1, so a plus b has to be 1. And if you're tangent to this curve, that means if you take the derivative of this, which is going to be minus bc sine of c pi over 4, now we're plugging that value in here, and we're taking the derivative, and the derivative of the cosine is minus sine, and we are using the chain rule. And so we have an equation here, an equation here. Now notice, my dear students, this is 2 equations and 3 unknowns. That means for there to be a solution, we can actually parameterize it. And by inspection, I can look here and I say, well, what happens if c is 2? Well, if c is 2, the sign is 1. And so it's 2 times 1. This is minus 2b is equal to 1. That means b is minus 1/2. So if c is 2, b is minus 1/2. And from this equation, we know that a is equal to 3 over 2. Again, we were to find one equation that works. Here I'm going, and you can see that it does have the tangencies that I predicted at the places where we had it. So that's the answer. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself, because self-care is important. And now more than ever, take care of each other, because we're all in this together. God bless you all, and look forward to seeing you in class soon.